My name is Jeff Condit, and I'm a Senior Principal Engineer with 9.Connects. I've been doing electronics engineering for more than 40 years in an extremely wide range of applications and all their varied aspects. Today I'd like to talk to you about a very simple device we usually take for granted, capacitors. Capacitors are ubiquitous. They're used everywhere. If they are so simple, then why would we want to talk about them? Well, because capacitors are simple, they are almost invariably taken for granted. And because of that, many engineers think of them merely as a capacitance and a possible voltage rating. And so unconsciously, they don't seek to understand their many nuances and limitations. These limitations are critical in many of today's circuits. So with that said, let's go back to the basics and talk about what's happening inside the atoms and molecules. Imagine an infinite empty space filled with nothing but containing a conductive metal sphere, and let the atoms in the sphere have an equal number of electrons and protons so that the charge is completely balanced. This sphere has no net charge on it, and so no electric field emanating from it. So if I place another charged particle, such as an electron near it, it is neither attracted nor repelled. I can move it up and stick it on the sphere without any force and hence without doing any work. But now it has a net charge. If I bring another electron into the space, it will now be repelled slightly. So I now have to do work to drag it over to the sphere and place it there. Thus, the sphere now has a charge on it in response to the current of the electrons being dragged from far away onto it. If a change in charge causes a change in the electric field, it causes a change in voltage. Thus, the sphere has a capacitance defined by C is equal to Q over V, which is derived from Q equals CV. And it looks like there's an error on my screen, so that really should be C is equal to Q over V. This is an example of absolute capacitance, but some people are bothered by the thought of absolute capacitance. So we can also ignore that. Let's instead talk about the capacitance between two metal objects like flat parallel plates. The same scenario holds true. By bringing one electron from one plate and placing it on the other, you get the same effect. As you do, charge builds up, and so do forces on the charge as you move it, taking increasing energy to move each one, and the voltage goes up. This, too, constitutes a capacitance. The absolute or vacuum permeability of free space is approximately 8.9 times 10 to the minus 12 farads per meter. And the relative permittivity is 1 by definition because it's the permittivity of free space. That's just kind of how much space gives you in terms of capacitance. It's a fundamental constant of the universe. But what if there is a way to amplify the capacitance by reducing the voltage developed when moving a particular amount of current between the plates? One way to do this would be if there were a substance which magically made a current flow in the opposite direction and in the process canceled out some of the voltage produced. These are called dielectrics, and the method of current motion is surprising to most engineers. So let's go to the next page. Okay. As shown in the upper left, let's assume we have an atom with the electrons circling around the outside and a nucleus on the inside. The electrons are negatively charged and the protons are positively charged. If we now place the atom in an electric field, as shown by the black lines going horizontally, then the uncharged atom will remain where it was because there's no net force on it. But the electrons will shift very slightly in one direction, while the protons, which are part of the nucleus, will move in the other direction. They can't go on moving forever because they're bound, but they displace with respect to each other by an amount roughly proportional to the magnitude of the electric field. The stronger the electric field, the more the differential displacement, as shown in the upper right. This displacement of electronics in one direction and protons in the other holds energy, acts to counteract the E field, and constitutes a capacitance. This means a lower external voltage difference is required to end up with the same energy storage than before. Thus, it acts like a dielectric and amplifies the energy storage for a particular applied voltage. Movement of negative atomic charges in one direction and the positive atomic charges in the other constitutes a current, something we call an atomic displacement current. However, remember that the atoms remain fixed in place and the displacement is extremely small, so it tends to be quite fast in response to sudden change and linear. A number of ceramic dielectrics act this way to create their electric field. The dielectric effect. The displacement within atoms is fairly small, and so the dielectric effect it creates is also fairly small. But there is another way that this displacement can occur. As shown in the lower left, molecules themselves can also be polarized, such as water. In water, the two hydrogen atoms are not on opposite ends of the molecule, as they are for CO2. Schrodinger's wave equations dictate that they are instead on one side, separated by about 107.5 degrees. This makes the entire water molecule polarized. The hydrogen atoms share their electron cloud with the oxygen and hence end up positively charged somewhat. And the oxygen atom receives some of the hydrogen's electron cloud, enhancing its negative charge. Thus, the whole molecule becomes polarized. In the presence of an electric field, water molecules will tend to rotate to align with the electric field. Again, this relative alignment of the positive hydrogen end and the negative oxygen end with the electric field constitutes a molecular displacement current. Molecules are typically much larger than atoms, hence much larger dielectric effects can be experienced. However, their rotations are much slower, so the effects take more time to occur and are less linear. Note that molecular displacement is slower than the atomic displacement, and therefore it's only effective at lower frequencies, frequencies that are lower than atomic displacement. So also note that rotating molecules tend to bang into one another because of their electric effects between them, and so they generate more heat in the process and hence are more lossy. Okay. So let's take another look at a couple of diagrams to see if we can make this more clear. At the top is a turquoise-colored atom showing its nucleus displaced to the right with respect to the electron cloud by an electric field pointing to the right. As shown on the left, halfway down, when the E field is 0, the nucleus and electron cloud are roughly concentric. However, when a non-zero electric field is applied, the positive nucleus and negative electron cloud displace in opposite directions with respect to each other, and this is called atomic polarization. The shifting of the charges as it is occurring constitutes a current and is called atomic displacement current. In the lower left are two sets of water molecules. The one on the left shows molecules randomly oriented, it hence is unpolarized. But the one on the right shows the water molecules all oriented the same way in response to an electric field, and hence is polarized. This is called molecular or orientational polarization. Further, note that being at room temperature means that all the molecules are all jiggling around in a constant state of change, and hence a more accurate statement is that they would be statistically oriented more one way than another. This induces thermal and voltage effects into the displacement current, and hence the dielectrics which rely on it. In the center is a depiction of two plates of a capacitor charged to generate an electric field between them. The molecules of the dielectric are statistically oriented in accordance with the forces generated by the electric field, which means that a lot of displacement current has already occurred during charging. That's why you would draw it the way it's drawn. The combined tiny fields of the dielectric offset the field from the plates, resulting in a lower voltage between them. A device which accepts a lot of charge but only develops a small voltage is said to have a big capacitance. Hence, what we are drawing is a way to make a big capacitance, because all of the tiny charges allow it to do that. In the upper right is a depiction of ohmic or unbound current, in which application of electric fields causes a continuous proportional flow of electric charges, positive in one direction and or negative in the other. But because the charges are not bound to an atom or a molecule, the current continues unfettered forever. This can be seen in the plot just to the right of it. The current just, once it starts, just continues, and is typical of Ohm's law current in a copper wire or ions in a solution, etc. Below that, however, is depiction of what happens when the charges are bound to an atom or molecule. When an electric field is first applied, the charges start to displace, and they can to some degree. But since they are bound, the further they move, the more restraining force builds up in the atom or molecule. Thus the current dies out, as shown in the plot to its right. This happens much more quickly in atoms than molecules. Okay. So let's change the topic a little and talk about capacitors in series and capacitors in parallel. First, let's talk about parallel. On the right, we see that capacitors in parallel have other elements to them. We know capacitors add, such that if we say we have a 1 microfarad and a 2 microfarad in parallel, the net after they combine would be 3 in parallel. But what about ESR, ESL, voltage ratings, and current sharing? The same voltage is applied to both capacitors, the complex capacitor that is, and for low frequency changes, the impedance of the capacitance dominates. So the current divides in proportion to the capacitances to keep the voltages equal. Thus the 2 microfarad capacitor will take about 2/3 of the current, while the 1 microfarad capacitor takes about 1/3. I say about because we haven't talked about ESR. The smaller cap may have a lower ESR than the larger cap. In cases of significant current, such as when charging or discharging or at higher frequencies, the proportions will change. It's the voltage across each capacitance plus its ESR which remains equal. Thus the current may not split exactly 1/3 to 2/3 during this time. It could be important if you're making something like an AC current divider. Sure, they will equal out if left at a DC for a while, but that is not the only application or usage of capacitors. So making that assumption is not valid. Remember, before you can determine the correct capacitor solution, you need to fully determine the purpose of each capacitor circuit and its requirements. At very, very high frequencies, ESL dominates. So at events like sudden steps in voltage changes across the capacitors, the relative ESL values will determine which current initially ramps up faster. Lower ESL corresponds to more rapid current ramp up on that capacitor. You probably won't ever get into it, but you could be trying to see an effect and using 2 capacitors to split the effect. In such a case, you would have to consider the ESL. At middle frequencies, far away from sharp voltages or large currents, the capacitance values will dominate and control the current sharing. Thus, if you put 2 capacitors in parallel, their capacitance will add under these conditions. But what if you use different voltage ratings? You can do that as long as you never go above the lowest voltage rating in the set of capacitors. Because if you do, you'll destroy that capacitor because it can't take the voltage. That is, however, costly and heavy because the bulk volume and weight and cost of a capacitor is typically proportional to its energy storage capacity at full voltage. Energy storage in a capacitor goes like the square of the voltage, so let's say if you parallel a 10-volt capacitor and a 100-volt capacitor, you can only operate them at 10 volts, otherwise you'll destroy the 10-volt capacitor. But at that voltage, you'll only be using 1% of the higher voltage capacitor's energy storage, and it's bulk. So it's going to be costly. You're just not using it. So let's talk about series. On the left, we see capacitors in series. We know that series capacitance is combined like the reciprocal of the sum of the reciprocals, such that, for example, if we have 1 microfarad and 2 microfarads in series, the net capacitance would be 2/3 of the microfarad. And we could go through that, but I'll assume you all know how to do that. But what about the effects of ESR, ESL, current ratings, and voltage sharing? For middle frequencies, the capacitive reactance dominates. And so with the same current flowing through both capacitors, the voltage changes divide in inverse proportion to the capacitances. Thus the larger 2 microfarad capacitor will end up with about 1/3 of the voltage change, while the smaller 1 microfarad capacitor will end up with about 2/3 of the voltage change. I say about because we haven't talked about ESR or leakage and their effects at low or high frequencies. The smaller cap may have a lower ESR than the larger cap, and in which case, during charging, the smaller cap's overall voltage portion may be a bit less, while the larger voltage cap's voltage portion may be a bit more, such that the resulting voltages are affected. Thus, the voltage may not split exactly 1/3 to 2/3 during this time, which could be important if you're making a precise AC voltage divider. Further, note that since the capacitors are in series, they will not equal out in voltage if left at a constant DC level for a while, as parallel capacitors would. We haven't talked about leakage currents. If the capacitors leak at all, which is typically true, the DC voltages on each capacitor will eventually seek some voltage based on the ratios of the leakage resistances, not the capacitances. These resistances are very high and very out of control. So you either need to add known bleeder resistors to swamp them out, or else you need to choose a voltage rating of both capacitors such that they can both individually be able to take up to twice the voltage rating of the pair. Again, this is costly and heavy because the bulk volume and weight, and to a large degree cost of capacitors, are typically proportional to the energy storage. We've said this before. I say twice because these things are only doing a delta voltage change. If one is fully charged and then you apply a change to the whole thing, the other one can go past its ratings. They're not dividing the voltage necessarily. They're holding the voltages that they already have. Again, take note, before you can determine the correct capacitor solution, you need to fully determine the purpose of each capacitor circuit and its requirements and the parasitic effects. At very high frequencies, the ESL dominates, and in a series capacitor circuit, the net ESL is the sum of the two. This increase in ESL, coupled with the reduced capacitance of capacitors in series, decreases its high-speed responsiveness. Is that something you want to do? Maybe it's okay, maybe it's not. In general, for capacitors in series, the voltage of each capacitor should be chosen to be able to withstand at least the highest voltage of the source circuit, unless special precautions are taken to assure they won't exceed their maximum ratings. In some cases, even more is required. In summary, it's rare to see capacitors used in series, especially in conjunction with bleeders in high voltage, except in conjunction with bleeders in high voltage circuits where efficiency and heat are not issues. Okay, let's go on a little bit. Enough of that. Let's quickly talk about a Bode plot. You guys have seen this probably many times. A capacitor is comprised, if we take a typical capacitor and say it's comprised of the capacitance, the ESR, and the ESL all in series, then we end up with something as shown in the upper left. Now, we could also say that there's a leakage current, which is like a resistor around the capacitor, and you could include that. We're talking about at high frequency, so I'm going to ignore leakage right now and just sort of lump its effects in with the ESR. Although in cases, if you're holding them DC and wanting to talk about it, it really should be treated as a separate element. So each of these things react in different ways. The resistance looks like a resistance, and is shown as at the blue line in the lower left. It's a little phasor diagram showing the complex vector. ESR is a blue line to the right. The ESL reacts in one particular direction because of its inductive effects. It's a red line going vertically up. The capacitance itself acts like a line going directly down. If you add those all together, you get a net effect of what the impedance would be. In a Bode plot, we plot the magnitude of impedance on the vertical axis. So if you look at it, you will see a black line extending from the upper right down to the lower left that says 1 over j omega c. This is controlled by the capacitance. As the frequency increases, the impedance of the capacitive portion goes down. You'll also see a red line going from the lower left to the upper right. That's controlled by the ESL, the inductance, and its reactance increases as frequency goes up. There is some point at which the black and red lines cross. Now, since these are equal but in opposite directions, they cancel, and therefore the impedance goes to 0. So if you look at the purple line that talks about the sum of the two, you'll see it follows the black line coming down, but then diverges below it and goes all the way down to in a dip, and then comes back up and follows the red inductance line up. So it follows the capacitance, it follows the inductance, whichever is higher. But right in the middle, it would try to go to 0. Instead, however, it's reaching down to a horizontal blue line labeled ESR. If you have a very low ESR, you can see these dips, okay? But what if your ESR is higher? Well, up above in this plot, you'll see a dashed blue line that says ESR prime. If you have a higher ESR, then the net effect is what you would see with the green trace. It starts by coming in from the upper left, follows the black line down until it approaches the ESR line. Then it turns over and goes horizontal for a while along the ESR. Then finally on the right turns and goes up the red ESL line. So this is typically what you will get out of a capacitor. And you need to kind of know what the ESL and the ESR are in order to determine what it will do. People oftentimes put a large number of capacitors of different values in, such that they have these different plots, but they shift them left and right in frequency by using larger or smaller capacitors. And in the process, if you put them all in parallel, you kind of can get a very low impedance over a wide range. This is used for doing things like trying to reduce the impedance of a power plane. If you guys are trying to do that, there's a really useful tool that is called the ICD tool that 9.Connects can help you with. So feel free to contact us about that. Again, it allows you to put in all sorts of capacitors of various types and materials, as well as specify planes and dielectric materials of the plane, and it calculates the capacitances and impedances that would result. So if you know what kind of energy sources you have on a plane, you can design a really robust power system. Continuing on, there are various types and shapes of capacitors. I've only shown a few here just for the sake of argument. I'll go through them quickly. If you take 2 strips of foil and intersperse them with 2 strips of, say, paper soaked in oil and roll them up, you get a cylinder. And because if the foil was shifted left for one sheet and shifted right for the other, the exposed foil on each end is from the 2 different sheets. So you can attach a lead to that, and presto change, you have a capacitor. Oil and paper capacitors were very common a long time ago. They're not really used much anymore except by audiophiles. But the oil had a fairly high dielectric constant, and they were pretty good. However, they're long. They were up to several inches in length, and then the leads had to come out because the bonding was poor to the ends of the capacitor. They ended up having to they did various things like piling extra epoxy or wax on the ends to try to make it stable, but you usually shouldn't bend it right at the end. You needed to go out a little ways before you bent it, and then of course it has to go down and through the board. So because of the long lead length and the long capacitance, plus the fact that there's a spiral inside, it turns out it has a very high ESL. So these things work well at high frequencies, normal radio frequencies, and even up to the lower VHF range, but they certainly would not work at UHF or any higher frequencies than that. But they were very cheap, simple, and easy to make. Later they decided they could make them more compact and better by solving the manufacturing problems, where they would just stamp out little sheets of dielectric and little sheets of foil, and then they would carefully make a stack out of them. And they could make them round or they could make them rectangular. But what they would do is then add leads onto that and dip them in things like capacity to make the little Chiclets caps or other kinds of things, or the radial caps. The radial means the leads kind of come out the side, radiating out from the center. If you lay those down, axials are so big and heavy that if you have shock and vibration, you have to stake them. Radials are a little bit better. If they're laid down, you might get away not doing it, but if they're larger, you definitely want to still stake them. And if they're standing up, they're still susceptible to a lot of shock and vibration. One thing they did with radial capacitors was to take some of the foil layers and basically coat them in silver, because silver has a very, very low resistivity at very high frequencies. And then they would take a block of mica, which has a planar cleavage, and then very carefully plane off very, very thin pieces of mica and put them in between. And so using that as the dielectric, they could make a capacitor that was really good. Mica has a dielectric constant of about 6, so it tends to be make a lot of capacitance in a small small place. Plus, it tends to have a very, very low loss. So putting those together, they made silver mica capacitors. They were really, really good. You can still buy them. They're used in some very high frequency places, but they're not a common usage. So. Okay, what about cans? With the advent of electrolytic capacitors, which form a thin oxide layer instead of having an actual dielectric medium, they ended up having to contain it in some way, and so they put them in aluminum cans and typically would cover it with a piece of plastic so it didn't short out to anything. You can get very short, squatty ones. If they're short and squatty, they probably do not need to be staked. It still may be good if you have extreme shock. If they're standing up tall, then shock and vibration can be severe, and you really, really do want to stake them. But can-type capacitors have become much more common. There are also some, again, oil capacitors still that come in cans. They're useful for very high voltage, non-polarized applications, such as, motor phases and getting things started. They still show up there. Then we come to what most everyone is familiar with today, which are surface mount type chip capacitors, which again are stacks of foil and stacks of dielectric all put together, and then they metallize ends on them and you stick them on a PC board. These are small enough that typically you don't have to worry about staking them down, and unless you get something that's stacked up very, very high. They make some capacitors that have a number of single capacitors all stacked vertically, and if you do that, you may need to stake those down. Since the leads are so close together and since they're directly soldered to the board, there's almost no leads, and so the ESR and the ESL are both very low, so these work very, very well at high frequencies. They've actually come up with a method in some capacitors to actually metallizing the long edges such that they're closer together, and those do even better in frequency. Kind of a short form factor of the same surface mount device. I do want to make one comment about these capacitors. Because they're flat, they lay flat on the board. So if you make two pads and you lay it flat, you have an issue with being able to clean underneath them. Now, we don't normally think about how do we manufacture these things and how we clean under them, but it's becoming a big issue. In general, like let's say you had something like a photonic detector which has extremely low currents and you need to integrate over a long time, even a tiny amount of leakage would make that circuit not function. So you need to clean it really, really well underneath them. Well, you can't generally do that because there's no space. In those cases, people are finding that they need to actually machine slots under them so that they can be cleaned. Usually you can do a little bit of cleaning if you make sure you do not put any solder mask underneath them and you do not put any silkscreen underneath them. You can usually get a small amount of fluid under there. But again, that's really difficult to do. If you run traces between the pads and put solder mask and silkscreen under it to make some little blips so that you can see it, you may well be high centering the capacitor on those pieces. So generally it's done a lot, but it's not really a good practice. So it's best to keep it really clean underneath, and if possible, take away the solder mask, take away the silk screen, make the silk screen go around the outside if you need it, and then if possible, put a hole in the middle or something for the fluid to drain through. There are also some very big capacitors, electrolytics, that can be like 6 inches in diameter and a foot long, and have many hundreds of thousands of microfarads and many hundreds of volts. They store so much energy that they can be dangerous, and if they were to short out externally or internally, they can create so much heat that they can actually turn gaseous and blow their guts out. So they put a vent on them, and the vent needs to be positioned in such a way that if it does happen, that it's not going to hurt a human being. So just be aware that there is a vent on the very large capacitors because of them being dangerous. Also note that usually on these cans, the outside of the can is one of the electrodes. So if you have something that's floating at many hundreds of volts and you want it to be isolated, say from the ground, you need to have an earth ground in your chassis. You don't want to just bolt it to the chassis, because the little bolting clips at the bottom are only sometimes not very well isolated from the capacitor body itself, which is again an aluminum can. There may be a little bit of foil over the mylar plastic over the outside, but you just have to be very, very careful. If it doesn't have the rating specifically that you need for isolation, you may have to mount it on an insulating block or layer. Okay, so it's important to know that capacitors are not ideal. In order to deal with that, you need to understand how they're not ideal, so we're going to talk some about this. And so I'm going to belabor this point a little bit because it's surprising to most engineers. So just understand that there are various ways people have categorized things, but they give us a false sense of security. For example, let's talk about temperature dependence. EIA has come up with a set of Class 2 temperature codes. Things like X5R and Z5U, etc., have three characters. The first is a letter indicating the lower temperature in the range. The middle character, which is a digit, indicates the upper temperature in a range. And the last indicates a tolerance. Now, the tolerance can range from plus or minus 7.5%, which is really pretty big, to a U down at the bottom, which is, again, from plus 22% to a whopping minus 56%. So with temperature, the capacitance can vary all over the map. So even though you buy a capacitor and it says it's a 1% capacitor, all that's telling you is that at 20 degrees C, you are buying a capacitor that has a value that is within that 5% or that 1%. But it doesn't mean it's going to stay there as temperature changes. Okay, so there are, over on the examples, you'll see a Z5U is again minus 22 to, plus 22 to minus 56 across its only 10C to 85C temperature range. That's not very good. It doesn't even hold it down to freezing, okay? So down at the bottom are some other types that don't fall into the EIA Class 2 codes. They're approximately equal. There's a C0G and an NPO. They're both 30 ppm per degree C, and they run from minus 50 C up to a high temperature. The NPO goes up to 150. The C0G is only to 125. But other than that, they are very, very good and stable capacitors. But what you'll find is they don't have much capacitance in them. So why are they good, and why is it they don't have much capacitance? It's because they do their displacement that creates their dielectric constant using atomic displacement instead of molecular displacement. The other capacitors that are much bigger tend to use molecular displacement, like an X5R. So let's look at the chart down in the lower left. First, the vertical axis is percent change in capacitance. We start over on the left around 0. Now, as we get up to as the temperature increases, this one shows the blue line is a TDK X7R material. And you see it sort of wanders up around 0, goes below and then up. But when we get up to about 90 or 100 degrees C, it dips way down to about minus 8% change of capacitance with temperature. That's standard for it. So obviously, if you can't tolerate 8% change, and you have to get up in temperature, you don't want that. Okay. It also shows another line, which is a competitor's X7R in red, and it goes down even further. I'm sure it was intended to show that theirs doesn't go down as far as the others. What I'd like you to note is that the blue line and the red line don't have the same shape, even though they are both X7R. X7R is not a ceramic. It's a temperature code, temperature tolerance code. Every manufacturer makes their own recipe for ceramics. They put different things into them. And so they find something that works for them that overall falls into the temperature tolerance ratings, and then they call that their X7R or their X5R. Also note the line, the green line that's right on 0 and stays right on 0 across all the temperature. That's a C0G. Again, it's very, very linear. It doesn't change much because it's doing atomic displacement instead of molecular displacement. A couple of comments about aluminum electrolytics. There are no real such standards, codes that I've seen from EIA or anyone else. There may be, I just haven't run into them, and they're not typically published when you go to a website to buy some. But they typically run about minus 20% to plus 10% from minus 40C to plus 85C. You can get some that go up higher in temperature, but usually their life goes down, so you need to be careful. But their tolerance is, again, plus or minus, tens of percents. So remember that as you talk about the temperature change. Aluminum electrolytics also exhibit bounce back or recovery of voltage, such that if you short the capacitor out, you'd expect the voltage to be zero. But if you remove the short, it's going to go back up in voltage. Why is that? Well, it's because it actually has a thin oxide layer that's generated dynamically by chemical processes that really acts a lot like a battery in essence. So you short it out, it discharges the battery, it's at 0 volts, but you put it back, the chemical energy stored in the chemicals actually continue to react and recharge it to some degree. It won't recharge to full amount, but also don't expect it to be completely dead after you've shorted it out. I suppose if you shorted it out for a week, it wouldn't bounce back very much. Okay, so how are capacitors non-ideal in other ways? Let's talk about what happens when you apply a voltage to it. First of all, the capacitance of capacitors decrease non-linearly with voltage. In the plot up at the top, you'll see that capacitance is over on the left and goes from 0 to about 5 microfarads. Across the bottom is DC voltage, which goes from 0 to 25 volts. So as the DC applied voltage goes up, all these capacitors start out at 4.7 microfarads, but they go down to some very, very low values. For example, there's an X5R 0805 that goes from 4.7 microfarads down to about 0.7 microfarads. That's a lot. That's almost 10 to 1. And that's as the voltage changes from 0 to 16 volts. It looks like it's a 16-volt capacitor. So you bought that capacitor and you thought you were going to make a tuned circuit out of it, or a filter that rolls off at a particular frequency. Well, think again. If it has DC across it, it's going to make a difference. So while these have capacitance, the initial value at 0 volts is great, and if you're driving it at 0 volts, you can probably trust that. But if it's going to have a DC offset, you need to be careful. You need to know what you're trying to do. Is the capacitance value important? If it is, then you don't want to drive it with DC, or you want a different capacitor. You can also see it in things like total harmonic distortion. Down at the bottom in the left, you'll see total harmonic distortion on the vertical axis at 20 dB at the top and minus 90 dB on the bottom. Minus 20 dB is not very good. Minus 90 dB is really pretty good. So, and the bottom, the horizontal axis is AC volts that you're driving the capacitor with, and it can be anywhere from 0 to 8 volts. You'll see up at the top a yellow line and a magenta line. Those are for Z5U capacitors. Again, a fairly cheap dielectric that has lots of capacitance and small capacitor. But because its capacitance changes with voltage, it will induce a large total harmonic distortion if you put an AC voltage on it. You run an AC voltage across it, and the current that it draws will not be of the sinusoid of the same frequency. It will have harmonics in it generated by the capacitance nonlinearities. Monocaps look to be about 20 dB better. Down at the very bottom, you'll see a green line and a red line, and those look really, really good down around minus 90, minus 95 dB. Those are polyester film capacitors. So if you're going to have an AC voltage, and you're going to want to make sure you don't introduce total harmonic distortion in a circuit such as, say, a sonar system or a Doppler system or something, then you really want to consider film capacitors and consider all of these effects. In the bottom over on the right, you'll see a capacitance change that runs from minus 100 up to 40 versus DC bias again. Okay, down at the green line at the bottom is a Y5V, and notice it's very bad. It goes from 0, changes almost 100% as the voltage gets up to just up to 6.3 volts. A little bit better than that, but it's still pretty bad, is an X5R. Then the other 4 up at the top are all sort of clustered right around 0. The polymer aluminum tends to go up a little bit, but not very much, a few percent, 2 or 3. The polymer tantalum goes up a little less and is kind of in between the red and the black lines. And what really looks good is the red line. The red line, again, is our C0G. Again, it's excellent. Again, atomic displacement versus molecular displacement. Okay, let's look at a few more examples of distortion. Again, in the upper left is 0 to 2% total harmonic distortion, 1 kilohertz, 1 volt type signal when the DC is varied from 0 volts to 16 volts. This is for a 0.1 microfarad Y5U. Note that it starts out around 0, then it goes up to almost 2% and then comes back down. So not only does it change, it's not linear. Okay. In the middle at the top, you'll see THD again of minus 40 dB down to minus 65 dB versus frequency. It's non-linear with frequency too. 10 hertz is on the left, 100 kilohertz is on the right. So as these capacitors go across the same frequency in the same way, note that the total harmonic distortion varies because their characteristics are acting more linear in some places and more curved in other places. Over on the right, you again have 20 hertz to 20 kilohertz in frequency. This is a Sallen-Key low-pass filter, and then we're plotting total harmonic distortion on the vertical axis. Here we go with the standard C0G that's really nice. 1206 comes across very low, about minus 105 dB, and then gradually when you get to the roll-off point, the total harmonic distortion starts to go up. However, if you are using X7Rs, then the green and the blue lines are much higher up there. They're almost in the 60 dB range. So you've got a lot. You've got 50, 60 dB of total harmonic distortion just by choosing a capacitor that is not really flat. If you need huge amounts of capacity and you don't really care that they're flat, then go with some of the molecular displacement ones. Otherwise, stick with the atomic displacement ones that are much better. Further, capacitors also are non-ideal in that they change with time, the hours of use. Down at the bottom, you'll see a plot. The blue plot is a Z5U. Notice that over its lifetime of 100,000 hours, it drops about 25% in terms of capacitance. An X7R is better. It's the green line. It goes and drops about minus 5% over its lifetime. And then again, up at the very top in red is a film capacitor. Note that its capacitance is excellent and stays where it should be over its lifetime. It's important to know all of those effects so that you can choose the right capacitor for what you're doing. Let's talk about another effect called dispersion. It takes time for atomic displacement to occur, but that time is very short. It also takes time for molecular displacement to occur, but that time is very long. So until this displacement is complete, the current is still flowing and the dielectric effect is not fully established. Hence, during this time, the dielectric is changing. So at different frequencies, we will see different dielectric constants, epsilon sub r's. Epsilon sub r rolls off with frequency in a way which is frequency dependent. That's what we're saying. So what ends up happening is because the molecules can't completely change and rotate in that period of time, if you're going back and forth at gigahertz and it can't follow, well, then you're acting more like a capacitor in a vacuum as opposed to a capacitor that's using this big dielectric constant. Okay, so what does that cause? Well, that causes effects as filtering, roll-offs, and delays. For example, let's say you take a long piece of coax or some other material, even a PC board, and you're trying to send a digital signal down it. Well, that digital signal is comprised of a whole range of frequencies. If you look at a spectrum, at least an order of magnitude worth of frequencies to get the bulk of the energy. So if your dielectric constant is rolling off in that area, it will affect the speed of propagation. And so the high frequencies see less dielectric constant, so they propagate faster down the cable than do the slow frequencies. So here's a rising edge. You're trying to send it from point A to point B, and at point B you want it to come back together and look like the right signal. But if all the high frequency edges arrive first, and then later on the bulk low frequencies arrive, then it's going to look all messed up, and it won't be a good clean signal. You can't clock on it, and you don't even know really when to sample. Hence, you need to make sure that for all the frequencies of interest associated with that signal, if you're trying to get them to arrive at the same time, that the dielectric constant is constant during that time. Very, very important thing to do, especially in PC boards. That's why people make Teflon PC boards and other such things. So just understand that, and you know, capacitors are not just discrete devices. They are the insulator in cables. They are that forms the LC, that's the transmission line. They are the dielectric in a PC board that react with your signals to give control to impedances. So capacitors are everywhere, and the dispersion effect is everywhere if you have frequencies at places where the dielectric constant is rolling off. Also, since capacitance varies with voltage, that can be a problem in many circuits. Take it into account. There are certain places it's used effectively. For example, there are in semiconductor devices, the more voltage you put across a diode junction, the narrower the junction becomes, and hence the capacitance across that at different DC voltages changes. That's if you use varicap and varactor diodes in certain circuits, tuned circuits, you can use a DC voltage to adjust them, such as in voltage control tuners or phase lock loops, etc. Another one we don't think about is your dielectric can change. If I have water is a dielectric, and if it's clean, there's not a lot of current that can flow in it, especially at high frequencies. But it is a very nonlinear molecule, as seen in our previous graphs. Hence, it's a molecular displacement type device, and moisture content can be a problem if it gets into your parts or into your PC board material. Not only can it cause manufacturing problems, it can actually create changes in capacitance in different spots where it might be and cause dispersion or other nonlinearities. So just be careful about water. We use water in a lot of our processes, so we need to keep it out. You may need to consider hermetically sealed parts or a conformal coating or things like that. All right, in summary, a couple of things. Up on the left is a table of capacitors. We've gone through most all of these. They are rated for, you know, the ceramic we talked about, the mica, silver mica, plastic film capacitors. There are the tantalums. Oscon is a type of polarized capacitor along with aluminum electrolytic. It kind of shows a capacitor range either being very low or very high. The ones that have a lot of capacitance tend to be the most nonlinear. The ones that have very low capacitance tend to be very, very good in terms of their dielectric effects. ESR will either be low or high depending on what things have to go through. Some of the electrolytics are fairly high because the electrolytic solution introduces some extra resistance, but they also tend to have a very, very large amount of area, so it tends to compensate by sheer surface area. And the leakage can be anything from low to high. Mica is a very low leakage type device, so is tantalum. The voltage ratings of various kinds, especially the ones in the upper part, can be very, very high. Ceramic material, plastic film, and mica all support many, many thousands of volts per mil. So even thin capacitors can support very large voltages. And the temperature range, of course, will vary with the type of material. Some plastics do not do well at very high temperatures. So if you're thinking about plastic capacitors, you need to make sure you find one that can go up to the frequencies of interest. Now, and also in general, the capacitors have different costs. So you need to kind of get a feeling for them. There's some really nice capacitors out there, but if you're going to be paying $20 a capacitor, it may not be able to make your cheap throwaway device. So get to where you understand all the different types of capacitors, their cost, and what their limitations are. And you can look them up for several capacitors in a place and decide whether you need them. Over on the right, just talks a little bit about the different kinds of electrolytic capacitors. On the left is a reference ceramic film capacitor that has a distance D between the plates. The voltage kind of, the storage kind of goes linearly across that dielectric because it's all constant. However, in the next one over, the electrolytic capacitor has a very thin oxide layer on the left side, which is on the positive plate. And the electrolyte, which is on the negative side, is attached to the negative plate. It's pretty well conductive, and as a result, it kind of acts like part of the plate. It's more resistive than the foil itself, but it's still pretty good. So when you do that, it turns out that oxide layer is extremely low. So it forms the dielectric layer, and therefore the voltage drop as you went across that gap, you would find it almost all occurs right at the positive plate. Then there are some supercapacitors, electrochemical type, that can form dual walls. They can be really, really good. They have certain areas where they excel because of having a couple of layers, but I would tend to say that they are very expensive. So double wall capacitors and pseudocapacitors, if you look at them in specialty applications, they might have some value to you in terms of their voltage or capacitance. Okay. Lastly, you'll see a lot of plots of various things like this that show voltage rating versus capacitance, to show where various types of capacitors fall. These are usually, they can be helpful, but they oftentimes also try to sell a new type of capacitor that somebody's generating, such as, in this case, the power capacitors, which are the furthest up and to the right. But they also can be useful just generally in seeing how things stack up. Manufacturers will oftentimes have these in their literature. And it just kind of, if you know that you have to go over 10 kilovolts, well, you probably shouldn't be talking about aluminum electrolytics, because you can't do it unless you go to some great extents to stack up and balance some arrays or do something like that. And also, if you're trying to look at capacitor above a farad, well, don't look at ceramic capacitors, because we're not going to get there. So these kinds of plots can be helpful. There are plots with things on the various different axes. There's a lot more we could talk about. Dissipation factor, on the loss tangent. Those things all derive from the frequencies at which these things can actually switch. If you have molecules that are trying to change because the frequency is in that range, then you end up having losses, especially in the molecular type dielectrics. So it's good to look at that. You have the ESR, which is almost a constant resistance, and then you have the other loss due to frequency, and that's where those come into effect. There are a lot more types of capacitors, a lot of specialty usages that we could talk about, but I think we're at the end of what we can do in this time. So with that, I think we'll have to call it a day, and thank you so much for joining our little webinar. If you have questions, please sure to get them back to us so that we can answer them. Thank you very much.